this computer. Thank you. All right, so now we are recording. So today is our second big meeting of CE-3305, Fluid Mechanics for Engineers. And because I don't want to use the chalkboard, and you don't want to breathe a bunch of chalk dust and go home. Of course, I guess the chalk dust is not competitive with the dust in the air from this morning's wind. Was anybody out in it? It was just like a Total Recall, the original movie. Okay, so let's go to class. Story of my life. So here's the announcement relevant to this class. Well, I copied this off the university website because I got emailed by somebody who said I had to do this. Basically, someone in our class tested positive. They're not here. They're in the hospital, but I think they're going to live because they were able to send emails. If you get a little sick, don't come to class, please. And that's why I was trying to get a window open and get some airflow. Let's share the virus with the math department. Give them something to put in their cabinets other than homemade buckyballs. And that's the only announcement about that. Let's go to class. Should be that one. Do it again for sure. For sure, it's a valley. There you go. There was a question: are you recording the videos? That'd be a yes. At least lesson 1 is up there, and lesson 2 will be up there. You'll need to tell me. You'll need to feed back to me if the volume's not good enough in the videos. There's not much I can do about it during one, but if I know ahead of time, I can jack with the microphone on the computer a little bit and make it better. So we will go back home. And there's a bunch of homeworks there, so take a look at them to be sure that you don't miss an opportunity to get some valuable points for the end of the course, so you can get that. So vowel. Everybody wants a vowel. Well, you have to pay for them on that TV show. So we've done that. Today's topic is not introduction. I think we got through all that last time. Yeah, what the problems look like. So basic fluid properties. So today we're in pages, I guess I could just, roughly pages 14 to 45 of the textbook for this class. So we'll look at intensive and extensive properties, some typical physical and thermodynamic properties. We'll look at one equation of state, which is called the ideal gas law. You've seen it before in other classes. There's a few other ones, but that one's is just a common one that's typical of every fluid mechanics class and textbook. As time permits, we'll get to viscosimeters, which I have spelled wrong. It's supposed to be spelled viscometer. And a little bit on vapor pressure and how they relate to barometers. That latter stuff, we might be pressed for time on that. So let's start with fluid properties. So fluid properties are the properties that fluids have. It's the barcode that's floating on it that tells you who owns it. Just kidding. Properties such as their density, presumably the color of the fluid, the flavor, although we don't measure those in engineering terms because nobody cares what hydraulic oil tastes like. It tastes bad. I can tell you that right now. You don't have to. There's the concept of an extensive property that applies to an entire system. and an intensive property, which is a per unit of system. For example, the extensive property of my body weight is somewhere around 165 pounds naked. I know that's a creepy picture. Get it out of your mind. If you were to take a core sample of me and maybe pull out a quarter liter of Dr. Cleveland, you pull it out, it would be whatever my total body weight is divided by that volume. We call that a density. I would be very unappreciative of that because if you took that much out of me, I probably wouldn't exist much longer. And those are the intensive properties. They're relating the same kind of information, but the extensive property applies to entire systems. So imagine a gallon of water. So there's a gallon of water right there, carefully labeled with the dihydrogen oxide label to let you know that it's dangerous. And it's got that little diamond-shaped thing that you see in every chemistry lab. It's got reds and yellows on it, telling you how dangerous it is to attempt to breathe that water, and that you need to call Environmental Physical Safety Division to dispose of it. Don't get caught pouring it down the drain. That'd be bad. It's just water in our drawing, so you can pour it down the drain. So we have that gallon of water, and we put it on a scale, and it's reading 8.3 pounds. So that's a very light vessel that the water is contained in. It's almost a zero mass container. Or we did something called tearing the scale, the words T-A-R-E, so you can put an empty container on it, tell it to tear it, and it'll subtract that weight off automatically. Out of that gallon of water, we're going to take about 30 cc's. We take that 30 cc's and we weigh it on another scale, and we find out it weighs 0.065 pounds. So there's the whole gallon, and then there's the 30 cc, which is about an ounce. Don't ask me how I know that. So when we weigh the entire gallon, 8.3 pounds, then we weigh the 30 cc subsample, 0.065 pounds. The extensive property of weight for the entire gallon is the 8.32 pounds. The extensive property of weight for the entire 30 cc's is 0.065 pounds. So I should have you been confused now, because we got pounds floating left and right in one SI unit just for grins. Now, if we were to compute the specific weights, which is the weight divided by the volume of the thing, we'd find out that the specific weight of a gallon is 8.32 pounds per gallon. A specific weight of 30 cc's is 0.065 pounds per 30 cc's. And then if we convert them to a common value, so we could either express them all on the cc basis or a gallon basis. It looks like I've converted cc's to gallons. We have the specific weight of 30 cc's multiplied by 128 would give us the weight in common volume basis of a gallon. And then we print those two weights. We find out that the specific weight of 1 gallon is 8.32 pounds per gallon. The specific weight of 30 cc's expressed in gallons is 8.32 pounds per gallon, as one would expect. The intensive property of water in this example is 8.32 pounds per gallon. So if I have 1 gallon, how many pounds do I have to lift to get the water in the back of the pickup truck to take to that South Pacific island that just blew up the other day? I'm going to send 1 gallon to, is it pronounced Tonga? I'm going to send 1 gallon to Tonga. How much airlift capacity do I need for that 1 gallon? It's up there on the field. Somebody beat bolts on that. Yeah, 8.32 pounds. But 1 gallon isn't going to help very many Tongese that are not croaked yet. We'll probably want to send several thousand gallons. So if I now want to send 1,000 gallons, stick it in the back of an airplane. Very inefficient use of airlift capability, by the way. How much airlift capability do I need for 1,000 gallons? 8,320 pounds of airlift capability. Whoever did 832, your math is bad. something times 1,000 is 1,000 of the things. Now, you thought I was trying to trick you. Say that, I'll get that later. I'll find some other stuff. So they're same value. So intensive properties are used in most fluid mechanics problems because they're a property of the fluid itself and not some fixed volume of the fluid. And then moving between total volumes and per unit volumes is relatively straightforward. But you got to be comfortable using both for two reasons. One, that's how it happens a lot of times. Secondly, homework problems have it in both ways. So let's look at the first one. Let's look at our friend density, or also called mass density, or mass concentration if you want to get fancy. It's simply the mass per unit volume of a particular fluid. The typical symbol is rho. It's easy to remember because you float boats in fluid and you have to row your boat. So that's the density, rho. And sometimes subscripted to identify a particular fluid. If you have a problem that has multiple fluids, you have gasoline, oil, air, water, spark, that'd be bad. So rho is mass divided by volume. Another property is the specific weight. That's the weight per unit volume. The typical symbol is gamma. It's related to density by gravitational acceleration. So gamma equals rho g. And the specific weight of fluid does depend on what astronomical body you happen to be on. For example, the specific weight of water on Earth is about 8 pounds a gallon. We go to the moon and weigh it, and that gallon of water is now going to weigh, any guesses? Mass of the moon, I think, is 60% Earth, so it'll be 6 times that, 4.8 pounds. We go to Mars, which I think is 8/10 of the Earth's gravity, and so on. So specific weight depends on where you are in the universe. Your lifetimes, that might actually matter. I will be long dead before we're sending gallons of water to the moon or Mars routinely. Another term is specific gravity. Specific gravity is the ratio of the density of a fluid to some reference fluid, usually water, but not always. In civil engineering, the reference fluid is usually water, liquid water, and a typical symbol is cap S, because they were out of cool Greek symbols for specific gravity. And it's shown here as a formula as either the density of the fluid of interest, I, divided by the density of water, or the specific weight of the fluid of interest divided by the specific weight of the water, with that implicit assumption that you're on the same planet when you make the measurement. Our next property of importance is, well, any questions at this point? I'm just reading stuff out of a book. Today should be relatively boring for most of it. Next one is the bulk modulus of elasticity. You have that in solids, which referred to how much of volume change you could achieve under a particular load starting at a reference volume. It relates the change in volume of a fluid element to a change in pressure. For liquids, it's usually quite large. For gases, quite a bit smaller. In fact, that's the definition of compressibility, is you change the pressure and the volume of the gas changes. It's essentially Hooke's law, which was that law you had in physics for springs. Remember, the force of a spring was K times the displacement for linear spring for a continuum element. It conveys how much pressure change is needed to affect an incremental volume change. And using letters of the alphabet, it looks like that. It looks like capital E is the common term for bulk modulus. And here it's subscripted with a V to indicate that that's a volume reference one. And it's simply the change in pressure divided by the change in volume relative to a reference volume. Dimensionally, it has units of a pressure. So bulk modulus is going to be expressed as a pressure. For water at terrestrial pressures and temperatures, its value is somewhere around 2.2 gigapascals. That's a lot of pascals, roughly 23 atmospheres. So we're at the bottom of an atmosphere right now. We're at 1 atmosphere. So you put 23 more heights of atmosphere above us. That's what the bulk modulus of elasticity for water is. For steel, cheap crummy steel from South Africa or wherever we get crummy steel from nowadays, it's 150 gigapascals. For special treatment steel, it's even higher, 200, 220 gigapascals, roughly 1,500 atmospheres. So steel is hard to compress, yet you can compress it. We all did it in the solids lab. If you've had the solids lab, if you haven't, you will. That little teeny blocks of steel, you put a bunch of load on it and it smushes. If you did that with water, it'd be hard to get the water to stay put long enough to smush it. If you did it with gas, you can't even load it fast enough. The gas gets out of the way. So I'm not stupid. I'm not going to use 2 metal plates and get smushed. In a practical sense, gas as we know it is compressible. Even the gas that you make after eating a good meal. Water's not very compressible, and we leverage that a lot of times in our practical use and treat it as incompressible. And steel is even less compressible than water. All the properties above are somewhat temperature dependent, and in gases, because compressibility is small, they're really temperature dependent, and gases get called as compressible fluids because they're compressible. So any questions on that? Did I confuse you all pretty thoroughly? Some of you have a deer in the headlights look on your face. It's either because it's 3 in the afternoon, your blood sugar is cratering right now, or I'm boring and I'm all congested, so I get to hear myself 3 or 4 times bouncing around in my head before it gets out to your all's ears. It's just like this morning, it's all this chalk dust. At least that's what I'm hoping it is. There's some thermodynamic properties that will rear their ugly heads sometime during this semester, so let's just visit them. There's something called the constant volume specific heat, and it's the amount of heat that's added to a unit mass of fluid to raise the temperature of 1 degree, and it depends on what unit system you're in, while the volume is held constant. Typical unit is C sub V, a typical symbol is C sub V. So let's go ahead and imagine a constant volume specific heat situation. We take a steel cylinder, hollow, weld plates on each end, and we fill it with some fluid of interest. And we take a torch, heat that until it gets hotter and hotter and hotter. Let's suppose the fluid is alcohol, and we didn't fill the thing entirely. We left some headspace. That way I can get to the vapor pressure at the end real easy. So extra bonus feature. So we heat that more and more. What happens to the alcohol inside that cylinder? We welded it so it can't get out. The only thing it can do is get higher and higher pressure. And the amount of heat that has to be added to it to make the alcohol 1 degree hotter is the constant volume specific heat. So we use constant volume specific heat to blow stuff up. Constant pressure specific heat is slightly different. In this case, we take that cylinder and we only weld a plate on one end. At the other end, we put a piston. Now when we heat it up, what happens to that piston? How your car works. It moves. And so that's the constant pressure specific heat. The usual symbol is C sub P. The specific internal energy is the energy the unit mass possesses because of its state of molecular activity. Typical symbol, at least out of the book I pulled this from, is lowercase u. Fortunately, that's a very popular symbol in the engineering mechanics world. It's also sometimes used for the x component of or streamline component of velocity. Sometimes uppercase U is used to represent the entire velocity vector. So usually the context should be obvious. If they're talking about thermodynamic stuff and they use U, they probably mean internal energy. If it is not thermodynamically obvious, the U probably means something else, or it may just be a vowel. The specific enthalpy is the energy a substance possesses because of its internal energy in any applied normal stress. So everything has enthalpy at some case. The typical symbol is H. I'm using lowercase h. I think it's usually cap H. And the enthalpy is equal to U plus P over rho. See a very similar structure to that when we get to Bernoulli's equation. So the observation that all these things are interrelated is not accidental. So no questions so far? Excellent. Now we'll move on to the equation of state. The state of a fluid is the value of all of its properties at specified temperature, pressure, and gravitational field strength. The word field spelled incorrectly. The ideal gas law is a relatively simple equation of state for gases. It's unfortunate that we don't have equivalent for a lot of fluid systems, because that would probably greatly simplify life. But it's also job security for us, so keep that in mind. So the ideal gas law, you probably, actually, I don't know how you memorize it anymore. I memorize it as Pivnerts. And in the college I went to, a long time ago, we made Pivnert bombs. I don't even know if that's a thing anymore. But it was a way to leverage the ideal gas law to overdose yourself with air and smoky stuff. And like President Clinton. Any other lies you want me to tell you? If anyone's interested, I'll tell you at the end of the class how to construct one. All you need is a 2-liter bottle, a little bit of screen, obviously something to burn in there. You get it started and you pull the bottle up until it just about leaves the water. And so now you have just created a smoky thing. Then you move the thing out of the way and then push it down. And you are leveraging modern chemistry. So one way is PV equals nRT is the usual way it's memorized. Pressure times volume is equal to the number of moles times the ideal gas, universal gas constant R times T. The other way is to express it as lowercase m over uppercase m, where the uppercase m is the molecular weight of the gas of interest. So we're assuming these are atomic gases. Monoatomic, diatomic, the gases aren't mixed. There are ways to handle mixtures that are pretty straightforward. So that's the equation of state. The equation of state for a gas also contains information for constant volume and constant pressure, specific heat. Because if we hold the volume fixed, we can calculate the Pivnert relationships, one particular temperature and a different temperature. That change in everything else is the constant volume specific heat. Similarly, we can hold pressure constant, make the same kind of calculations, and we get constant pressure specific heat. So gases are really nice because of that. Things like water aren't so nice because they have a pretty high specific heat going from 0 degrees Celsius to 99.98 degrees Celsius. Then they flash to vapor, and it doesn't take much additional energy to make that change occur. And then they stay at vapor for a while, which is called steam, and then you can get superheated steam, and water's a tricky substance. So we've seen the equation state for gases, ideal gas law. Questions on that? So I guess in our first exam, we'll say, in your own words, describe how to make a Pivnert bong. I'll show it to the boss. And then you'll be looking at another faculty instructor for the rest of the semester. So let's not do that. Pretty sure I just violated all of Texas Tech drug and alcohol policy right there. You figure it out on your own anyway. What is viscosity? Viscosity is how sticky a fluid is. So things in your everyday life that are viscous. Syrup, when you go to IHOP after a night of ordinary beer bong, and you get that syrup, that's an example of a relatively viscous fluid. If it's kept in the cold, you pour it, does it come out of the bottle fast or slow? It comes out slow anyway. You get it really cold and it's really slow. And it's an old expression among working people, you're as slow as molasses on a January morning. Usually uttered right before you fire the employee and try to find someone else. Fluids that are really slippery, on the other hand, water, oil when you're trying to keep it off of something, and so forth. And that property of how slippery it is called its viscosity. So we will quote it from somewhere. Viscosity is a property of a fluid that relates the resistance to motion when it's in a very thin layer when a shear force is applied. So this somewhat useless definition taken from a fluids book is trying to convey how fluids deform under shear, and more importantly, the rate of deformation. So let's imagine steel sheet that would cut with a shear, hence the name shear force, like scissors. If you want to cut a steel sheet really fast, you have a set of shears. Some of you may have done this. You know, those shears are about yay long. To cut it fast, you're going to need a whole lot of force. You're going to need to be bigger than Mr. Carter, probably younger too, before you can cut it really fast. If we use the same shears on a plastic sheet, it doesn't take as much force to cut the sheet at the same speed. If the shears can't actually cut it at all, then you apply all the force and they bend and deform. I had a 4-foot set of bolt cutters that I used to cut a chain once. I was authorized to do it, and they had a heat-treated chain. It destroyed my bolt cutter. I got the, about to use a bad word. I got the thing cut, but I destroyed a set of bolt cutters doing it. So, you know, if it can't cut it, that's too bad. Back to our story. So this solids analog is analogous to viscosity. That steel sheet and an equivalent thickness plastic sheet have much different viscosities as far as cutting them with a set of shears. Plastic, not very viscous. Steel, really viscous. Hardened steel that breaks your bolt cutters, really, really viscous. So now let's get back to fluids. Here's our drawing of a fluid deforming under a shear stress. So we start with this rectangle right here. Oh, that was stupid. Don't do that. Hope that comes out on the video. That was a sigh of frustration for those of you out there in TV land that are listening. We have this rectangle where the cursor is going around. Let me do that a few times for the video. So it should be making you nauseous now. And then we apply a force to the top of the fluid somehow. And at the bottom of the fluid, it's just sitting there all nice and happy on a plate. And that force moving to the right starts to deform the fluid. If we divide that force by whatever the contact area is, we have a shear stress. That's what this tau of yx is indicating. And a little bit of time is allowed to pass and the fluid deforms a distance dl. That's that right there. And it's also deforms by this angle of d alpha. And ignore the huge mind scourge here is that if the fluid's deforming like that, those plates should be getting closer to each other. We pretend that doesn't happen, that everything's all small and we get away with it. Your textbook actually draws them getting closer to each other without any explanation of how we're going to account for that. So we're just going to pretend that it's not a big deal, at least initially, so that we can talk about things in terms of the geometry of dy, d alpha, and dl. If we look at that shear stress, tau yx, that's equal to the limit as the contact area goes to 0 of force divided by area, df over dA, which is equal to df over dA, or the derivative force with respect to area in the limit. That rate of deformation is the limit as delta t goes to 0 of the change in alpha, that angle, divided by time, which gives us d alpha dt. And no doubt you have anticipated that if there's all that garbage there, there's going to be some more equalities going on to somehow relate alpha to something useful. And indeed, you are right. The rate in terms of the element geometry, how fast that dl is changing, is equal to dv dt, where dv is the velocity of the top layer of the fluid. You can relate that to y and alpha, as shown. We can observe that the tangent of alpha is dl over dy. Hence, we can relate the two and find out the change in velocity with respect to thickness of that thin layer. So moving from the bottom up to the top is equal to the change in alpha with respect to time. And in the limit, we get the angular deformation rate, d alpha dt, is equal to the velocity gradient, dv dy, in that thin layer of fluid. And that rate is related to this velocity profile, and we will make some statements based on that. If that angular deformation with respect to time is proportional to the shear stress, then we have something called a Newtonian fluid. It means that the shear stress is proportional to dv dy, and the constant of proportionality is called the absolute viscosity. The usual symbol is mu. That's the sound a cat makes when you apply viscous shear to its tail. Not really, they usually turn around and bite. If it's not proportional to the shear stress, that's called a non-Newtonian fluid. In the case of a non-Newtonian fluid, we have something called the apparent viscosity, which is actually a sneaky trick of calculus. We'll replace everything in front of dv dy with a power law model, including dv dy, because usually a power law is a pretty good explanatory model of what's going on. And we call that whole group of terms the apparent viscosity, mainly so that we can use the term viscosity everywhere else. And so for non-Newtonian fluids, the viscosity term is replaced by some function which is called the apparent viscosity. And naturally, we only measure it at a couple of points of interest. So it's often not a huge deal. It is a huge deal in things like paint, oils, lubricants, and stuff like that. But in civil engineering, we're dealing with water and concrete, and water that has little wiggly things in it that make you sick. It's not as a big a deal. Sewage is non-Newtonian, but not very non-Newtonian. It's Newtonian enough for practical purposes to treat as water, with the exception, don't drink it. It'll make you sick. Okay, let's make sure I didn't leave anything important out. Relevant trigonometry, absolute viscosity, a little bit of typesetting. I will often refer to that as the cross-layer velocity profile. When I say it, I think I made that up for these notes. I doubt that anybody else in the history of the world's ever used that. And that's to distinguish it from velocity profile when we get to bigger scales, like pipes and streams and stuff. The ratio of the absolute viscosity, or the apparent for that matter, to the fluid density is called the kinematic viscosity. I don't know how that name came about. Your book might have better information on that. And the usual symbol is mu divided by rho, and the kinematic viscosity has dimensions of area over time. So the usual way you can tell, so look it up in a table, you do your problem, you get the wrong answer. Somehow you have the right answer. Problem's a lot easier to do if you have the answer. And then if you go back and replace it with the kinematic viscosity, you get the correct answer. That's how you can tell the difference. But if they tell you what the units of viscosity are, the giveaway is if it's area over time, so something like meters squared per second, that's a kinematic viscosity. And regular viscosities have, so that's length over time over many, I think have, force times time over area. So it's shear times time. So it has things like, you see, stress is pounds per square inch and time per second. So something like pounds per square inch per second, or newtons per meter squared per newtons per meter squared seconds would be an absolute viscosity. They're weird units, you don't use them every day. It would be fun to mess with a Starbucks server, a barista, or whatever they call the people behind the counter that make your crummy coffee and take the money, to ask them for what's the viscosity of that. Actually, I wouldn't suggest to do that because they might actually know. There's a lot of PhD physicists that are serving coffee. Okay, some general comments. So viscous effects cause a velocity gradient to form in the thin layer of fluid. And here's a cartoon that's trying to show that. So imagine you have this plate right here, stuck out there in the middle of space, nowhere, and you have a fluid coming at the plate, initially has a uniform velocity. So it's out there in the world of plateness. And then as it hits the plate, the fluid at the plate fluid interface down here has to engage in no slip condition, otherwise it'll be kicked out of class. So it starts to drag behind, but these fluids up, this layer up here doesn't know that's happened yet. And so as we move down the plate a certain distance, we see that the layers that are closest to the plate have been slowed down by the fact that there's a plate there. Think of friction. Think of trying to negotiate traffic in, say, Dallas at 5 in the afternoon. And as you move away from it, these ones haven't been communicated yet. And so we form this gradient. And if we were to look at a little fluid particle somewhere in here, we'd see that there'd be a shear stress on the bottom, kind of pushing to the left, and a shear stress on the top pushing to the right. And those no longer have the same value. The one on the top is a little larger than the one on the bottom. So it's starting to cause this deformation, which we've already explained with that d alpha dt. We can use this knowledge to do some actually practical problems regarding viscosity. We'll look at the change in velocity over the entire profile. So from one side to the opposite side, or in this picture, from this plate to a plate up here. And that's a lot how it gets used.
One question.
Yep.
So that means like I had like a river and it's like an ideal river, like perfect flat bed over however long. That means the top is moving faster than the bottom. All the way across.
It does indeed. That's what viscosity means. And actually, real river has that property too, not quite as linear as here. Since you brought that up, if this were a river and we were looking at it sideways, where would the biggest velocity in that river be? If it was all nice, fully developed flow.
Like inside the river?
Yeah, you're looking at it from the sides. Not quite. It's a little bit below the top. No, it's the way it is. USGS told me so. I saw it on the internet. It gotta be right. It's the peak velocity is 0.8 from the bottom. It's not quite at the surface. It's real close to the surface, but it's not quite at the surface because of the frictional effect of the air. So it's like it's in a pipe. One side of the pipe is made out of river bottom. The other side of the pipe is made out of air. Yeah, fluids are confusing things. Yeah, if it's the business school's that way, if it gets too much for you. That was a slight on the business people, not on y'all. I have other ways of being mean to y'all. So the no slip condition is something that's been deduced from experiments. So here's my personal opinion. You don't get that very often. Oh, and it looks official because it's in a note box. It's an assumption that the velocity vanishes at the contact interface. Keep that in mind when you take other classes. It's quite possible that slip actually occurs at small scale. However, despite my disagreement with its existence in the real world, it's a really useful and accepted boundary condition, and there's no point to fight it now because all you'll do is get laughed at. But there is no reason why, at a contact point, a molecule has to stay put. There's no reason why it can't slip, other than it really screws up the arithmetic. So we'll say it doesn't slip so that our logarithmic profiles go down to 0 at the point of contact. So let's do some problem solving just for fun, because it's hot. It's a hot afternoon, and you all need to fall asleep so you can share your breath together and get your viruses all good and spread. So here's a handworked example to illustrate velocity concepts in the problem solving protocol. So we'll start with a problem statement. Let's imagine we have a 1 meter by 1 meter by yay thick block. I don't know how thick yay is. Weighs 25 newtons. Those are ordinary newtons, not fig newtons. It slips down a 20-degree inclined ramp at a speed of 2 centimeters a second. About an inch a second. That's not particularly fast. It's a block where a bullet, I would be fine with a bullet coming that fast. It might still hurt. 25 newtons is a pretty good sized bullet, but it probably wouldn't penetrate and kill you. The block is lubricated by a thin film of oil, which has viscosity of 0.5 newton seconds per meter squared. Is that an absolute or a kinematic viscosity? Probably an unfair question, because that's depending on short-term memory, which none of us have anymore because we have the internet. It's not area over time. It's force times time over area. So it's got to be an absolute viscosity. How thick is the oil? Admittedly, that's a stupid problem. Who cares how thick the oil is? But that's the problem. A more useful problem would be you have a known thickness of oil. It's sliding down at this speed. What's the viscosity? That would be a viscosimeter, which we'll see at the bottom of the presentation. But we'll go ahead and deal with it as is, because otherwise you have to take the class again until you finally get done with school and go out there and make the real cash. So our next step would be to sketch the situation. So there's my first sketch right there, my 25 Newton block sliding down an oily ramp at 2 centimeters a second. And where one can see that in real life, that looks an awful lot like an Amazon warehouse to me. These blocks are all sliding into the robot to get on to the UPS trucks so that they can be thrown on the side of the road on a snowy day. And because we have taken engineering mechanics elsewhere, we know that when in doubt, draw free body diagrams of everything you can imagine in hopes that there'll be some enlightenment there. So first is our free body diagram of the block itself. So we see the block I've drawn there. We're wise. We've selected one of our axes to be parallel to the plane. Select our other axes perpendicular to that, because that's what we're taught to do. So that x-axis forms an angle of 20 degrees to the horizontal. With that, we know that the weight vectors, the weight of the block by definition points straight down. So there is a component to the weight vector that's conferred by the slope of the block, and there's a component of the weight vector that acts in the y direction and doesn't participate in this given volume. What's keeping the block from accelerating off to the left of the picture? Our friend, the frictional shear force. F sub tau. And we'll make a free body diagram of the layer of oil. Obviously not to scale. So there's my oil layer, and I'll arbitrarily pick a point on the leading edge of the block and a point at the x equals 0 axis. I know that the block is sliding downhill at 2 centimeters per second, and I have to observe that there has to be no slip condition to each end. Otherwise, we can't get an answer that agrees with the book that I sold. So that's an important observation. Does that make sense to everyone? And don't just trust it because it's up there. I mean, if that works for you, that's fine. There's no slip at the oil block interface, and there's no slip on the inclined plane. So at that instant, the velocity at y equals 0, because of no slip, is 0. The velocity at y equals whatever the oil thickness is at the leading edge of the block is feedback. That's the velocity relative to the block is 0, but the actual velocity is, yeah, it's moving with the block, so 2 centimeters a second. So there are our sketches. We have a macro scale condition, which is the block, and the micro scale, which is the fluid layer between the block and the plane. The second sketch is the vital one. If you don't get that, the rest, none of the rest doesn't make sense. No slip here, no slip. I chose the leading edge because it's convenient, but we could have chosen a point right there. It's also moving it 2 centimeters a second downhill. Then we list our knowns and unknowns. So what do we know? We know the weight of the block is 25 newtons. The angle of the deal is 20 degrees Celsius, I think. 20 degrees of arc. The viscosity of the oil is given as a half Newton second per meter squared. The contact area from the drawing is 1 meter by 1 meter. So we got 1 meter squared. So whoever created this did it to keep the arithmetic really simple. Unknown. We don't know the thickness of the oil and the velocity profile. What are our governing equations? Well, the usual F equals ma, E equals mc squared. The sum of the moments about somewhere is 0. At least that'll work for statics. The definition of viscosity, shear is equal to mu times dv dy. And the definition of shear itself, which is force divided by area. So those are the necessary equations that we have to work with. So let's proceed with the analysis. So when in doubt, go from easy to hard. We probably can analyze the block. So we look at the sum of the forces on the block, and we immediately observe that it's a constant velocity, which tells us the acceleration, at least in the downslope direction, is 0. You know that because it's written up there. From that, we can equate forces to one another. We have the weight times the sine of 20 degrees minus the shear force is equal to 0. So the shear force is equal to the weight times the sine of 20 degrees, which equals tau times the area of the block. So the shear stress times the block area will recover the shear force. Now we'll analyze the oil. We'll assume it's Newtonian, because otherwise we're stuck. And we will write the expression of what shear stress is in terms of viscosity. So that's basically the definition of viscosity. Tau is equal to mu dv dy. Multiply both sides by the contact area. Tau times the area is mu dv dy times the area. Substitute in the value of tau times the area, which is w sine 20, equals mu dv dy times the area. Rearrange to isolate the thickness dy. It's mu dv times the area divided by w sine 20. Substitute in numerical values. Keep the units floating around. And at some point when you go home, you might want to check my arithmetic. I can't remember if this one still has the mistake in it. So like y'all, I tend to get decimal points in the wrong place. It happens. I'll take points off on your homework and exams when you do that, as you should take points off on me if I've done this one. But I come out with 0.000177 meters or 0.18 millimeters, which isn't very thick. That's a very thin layer of oil. So as a discussion, because I'd like you all to get the habit of discussing your results, you'll get really sick of doing it quickly. Your discussions will get shorter as the semester progresses. I'm aware of that. That's cool. Get in the habit of doing it. The problem required the use of engineering mechanics to find the equilibrium conditions for the block. There was an implicit Newton's third law of the force of oil on the block, force of block on the oil. No slip condition at top and bottom are the most important observation. And we assume Newtonian, we don't have enough information for non-Newtonian. And that's an example of applying viscosity in a somewhat realistic case. Again, the last thing you'd ask is how thick the oil is. That's stupid. The more reasonable question would be, I'm sliding my 25 Newton block down the inclined plane. I've poured the oil in. What's the viscosity of it? I'll do it again with water, so on. So homebrew viscosimeters. Just for fun, we can also do it in radial geometry. So this is a similar example of what's called a viscous clutch. This is how your automatic transmission works, although they're a little bit more sophisticated than T plates with oil between them. But fundamentally, that's all they are. So viscous clutch is made from a pair of closely spaced parallel discs enclosing a thin layer of viscous liquid. Develop algebraic expressions for the torque and power transmitted by this pair in terms of liquid viscosity, radius, disk spacing, the angular speed, the input disk and the output disk. Also develop expressions for the slip ratio, determine the efficiency in terms of the slip ratio. So you see a problem like that. Are you immediately terrified? Good. That's a mechanical engineering problem. We don't do clutches. We buy them. I pay for that. But this is what your transmission repair person, the actual technician that fixes your car, goes through. They pull out a greasy piece of paper and they do these calculations to figure out how much to charge you. Automotive repair comes in $300 increments. So it just depends on how many integers they can justify. So here's our drawing. We have an input plate, an output plate. We've got a viscous fluid between it. The obvious question is, why isn't the fluid pouring out the bottom of it? This is all enclosed in a housing. And what do we know? We know the input angular velocity, omega I, the output, omega 0, the disk radius, cap R, the spacing, A, and the viscosity. Our governing equations, some of the moments about in origin is 0, which is the statement of constant angular velocity. The definition of viscosity is a little different in this case because we have the dV dy part, the udV dy, that's unchanged. But the shear is changing with position from the axis of rotation. We get further away from the axis of rotation. Things have a greater linear velocity. They have to keep up with all the stuff on the inside. So that is a function of position. We have the definition of power, which is work over time, which is force times distance over time. So there's our problem statement knowns, and our unknown is the torque transmitted, the slip ratio, and the efficiency. Frankly, if we can find one of those three, we can find the other two. So just like before, when in doubt, draw free body diagrams of everything imaginable. This time we are looking at the into the disc coming at you, about to hit you in the face. And I have it rotating counterclockwise in this drawing. And the disc has a radius of cap R. And here's our input angular frequency, omega I. And we go out to the edge, and I'm going to replace all those distributed forces with equivalent point loads at the edge because it's just easier. So I have a viscous force pushing one way, and I have the drive force pushing the other way. We'll take moments about this axis of rotation, and the sum of moments about 0 is equal to the angular, shit, I forget what HO is. But the drive torque, the force of the drive times the radius is equal to the viscous force times the radius. That's a time derivative. I remember, I haven't done a dynamics class in a long time. So I'm forgetting what my letters of the alphabet are. But that's a constant, oh, that's momentum. That's angular momentum, a constant angular momentum. And now if we look between the discs, we have almost the same picture as the block sliding down the plane. we have zero slip in each disk face, unlike a real train. And we'll apply that requirement on each disk face in order to find the variation of velocity with spacing, but it's going to change depending on whether we're at the axis of rotation or we're out on the edge of the disk. So we have tau as a function of radius is equal to mu dv dy as a function of radius, and what's going to change in radius is the velocity. We know what that is. The velocity as a function of radius is r, the distance from the axis of rotation, times the change in angular frequency of the input and output disk, which is r delta omega. For that information, we can express dv of r dy as r delta omega divided by a, the spacing between the disks. And recall what our formula is for shear force. Now we get to integrate things. So we need the area over which that occurs. So we have to integrate from the centroid out to the edge. dA is 2 pi r dr. Now this should be bringing back horrible memories of statics. The differential force is tau dA, which is mu r omega, r delta omega over a times 2 pi r dr. The differential torque is r times the force. So r times the differential force, which is mu, r cubed, a omega over a, 2 pi r dr. Finally, we integrate the torque from 0 to cap r. We're integrating that Rascallian right there. We come up with torque is equal to mu delta omega 2 pi over a r to the 4th power over 4. And finally, we can express the viscous torque in terms of the drive torque. It's just the same formula. Now we can find the power and analyze the output disk. I'll let you do that on your own. We'll see that the power has something to do with radius to the 4th, which is why automatic transmissions don't get very small. They have to have a certain radius to them. And they have stators, and they need to flow that and move the flow around inside the transmission. So that is the same principle as the block sliding down the plane. We made it much more complicated by changing the geometry and changing the question. But it's the same principle. The viscosity is what transfers power from the input disk to the output disk. The viscosity is what transfers friction from the fixed plane to the sliding block. A little bit more arithmetic there, and we are done. Okay. So this is a complex problem. You can expect that on a 10-minute quiz in the future. Just kidding. This is a fairly complicated problem. It involves two geometries, radial in the plane of the disk and linear between the disks. We had to integrate, so it forced us to use calculus, which, let's see, by now you're juniors, so you've been out of calculus for about a year. So you've forgotten quite a bit of it, I would imagine. And again, it helps to have the answer ahead of time so you can work from each end of the problem, just like you did in math class. Although they'll never admit to it in this building, so there's chalk everywhere. And then figure 27 is the result in useful units in a discussion. So each problem part is pretty straightforward. Overall, that would, at first glance, appear to be a really hard problem. Something you couldn't do 10 minutes before it was due. I couldn't do it 10 minutes before it was due, even if I had the answer to copy from. I don't think I can write that fast. But the block sliding down the hill is pretty straightforward, right? It's the same problem, it's different geometry. So when the geometries get tough, copy from somebody. You need more time. You need more time to think through it. Okay, let's look at some liquid properties. So the other properties are properties of fluids, and liquids are a type of fluid, but they have extra special bonus features. One such property is the surface tension. The usual symbol is sigma, lowercase sigma. That's that funny looking thing right there. The surface tension is the force per unit area required to separate two fluids. It's usually measured with something called a ring tensiometer. I'll go ahead and I'll take the link in a second so you can see what a picture of one looks like. And there's a few other ways to measure surface tension. Dimensionally, it's a force per unit length, and it's one reason why liquids will rise up capillary tubes or seep into porous material. Basically, the way your sponge works at the house is because you took this part of the fluid mechanics class and learned about surface tension. And that's how come it can suck things up. It controls how liquids spread on its surface. So if we were to take ordinary automotive glass, so here's the picture of glass, and then put a drop of water on it, and think back to the windshield of your car. When it's really filthy and it rains while you're driving, does the water beat up and go away, or does it just kind of get there and obscure your vision? It kind of gets there and obscures your vision. That's because in that instance, the glass itself is pretty much exposed to the air-water interface. So the water is a wetting fluid in this case, so it's trying to spread over glass. Now, while it does that, it doesn't hurt anything except your vision. And I don't know about you, but I find it extremely hard to point the automobile correctly when I can't see where I'm going. It's even worse at night. But if we just go to the store and get some Rain-X, which is essentially it's a wax that you put between the glass and the air, when the water hits that wax, it beads up. It forms these beads and doesn't want to spread out. And then if you're going fast enough, it'll blow it out of the way and everything's fine and pretty. You don't even have to use windshield wipers. If you're like me and you don't change your windshield wipers as frequently as you should, you depend on Rain-X to handle most of the rainfalls. And then if you can't see and you know you have Rain-X on it, what's the next thing to do? Go faster. Try to blow the things off. And this angle at the interface, if it's less than pi/2, it's called a wetting fluid. Greater than pi/2, a non-wetting fluid. Now let's go look at some ring tensiometers. Hopefully they'll have pictures of them. So there is a ring tensiometer. So we got a fluid there. It's green. I think it's probably bond, the environmentally approved bond that you use for cleaning ducts off in oil spills. Not to be confused with palmolive for soaking your hands. That's way before your time. But that was a TV commercial. So this ring is lowered into the liquid, and then it's slowly pulled out. So there's a force balance, just like an analytical balance that you have in a laboratory. It's used to pull the ring out. So it can keep track of how much force is required to get that ring to separate from the fluid. And there's some human interaction involved. You have to tell it, yeah, it's separated. And then it will record the amount of force. The length of that ring is known because the people that build these things took geometry. And so the length of that ring is, anybody? It's a circle, looks like a circle to me, right? Ring, circle, same thing. So what is the circumference of a circle in terms of its diameter? Oh, you've got to be kidding. Somebody say it's got something to do with pies. Yeah, okay, cool, thank you. It's got something to do with pies. Probably two of them times the diameter. So the diameter is just the distance between these two vertical risers. You measure that with a tape measure. You don't want to use anything more accurate than that. We're talking precise measurements to micrometers. We'll measure it with a tape measure. Or maybe even a mask. It's like 1/10 of a mask across. But that's how the ring tensiometers operate. And there's what they look like when you put them in a fancy case. So that ring tensiometer that any one of us in this room could build ourselves, probably for less than $20. The hard part would be getting the weights to put on a balance small enough so that we can actually determine the force it takes to separate the ring. We take all that, we put it in this fancy case, and we charge $2,200 for that without the electronics to do the readout. Good work if you can get it. So there it is fancy, there it is up close. And here would be, when I went to school, this is what we had for ring tensiometers. All it is a balance that pulls the ring out and has a way of recording the force right at separation. But as soon as the ring separates, there's nothing pulling it down. So all you're doing is lifting the weight. just like in the materials lab, when you smush stuff, it knows when the stuff under compression has failed. And it detects that sudden acceleration and stops the instrument and records it. Same with this, only going the other direction. Ring tensiometers. Everyone should have one in their kitchen. I have no idea why. That just sounded like fun to say. So, viscosity, properties. All right, so let's look at another way one could conceivably measure surface tension. Would be to look at the capillary rise in a capillary tube. So when you go and get bled at the doctor's office, I don't know if they still do that. I've got fancy machines. They used to stick your finger in a big ass old knife, and they put this little glass capillary tube and suck blood up into it. Has anybody experienced that recently? Ever? And you go into some amateur doctors, tell you what, if you don't bleed every time you go to the doctor's office, you're doing something wrong. Because they pool all that blood and they sell it out of the back of the office at the end of the day to the blood bank. Okay, that serves me right for being a smart ass. Let me shrink this just a bit. Well, it almost fits on the screen. So in liquid, I'm using water and glass and air here as an example. But any tube of relatively small diameter stuffed into a liquid, the liquid will either rise up the tube or get pushed down a little bit. So for example, if we take a glass tube and we shove it into a pool of mercury, we'll have to do that imaginary now. You can't do that in real life. We'll all go to jail. The EPA cops will show up. And remember the EPA cops in Ghostbusters? That's what will happen. But if you were to shove it into mercury, the actual water level. I didn't know the EPA cops got here so quick. You'd shove the tube down and the mercury surface would go down. Mercury is non-wetting with respect to a glass air system. Water is wetting for a glass air system. So if we put a glass tube of small enough diameter, I mean, if the glass tube is as big around as me, we wouldn't be able to see the capillary rise. It wouldn't be very big. But a small enough tube, it goes up a pretty significant distance. So we can measure the height of that rise through the surface tension concept, apply a force balance column of water above this elevation right here, and equate the weight of the bit of water to whatever the surface tension forces are acting on the water. So if we write a force balance, we get the surface tension force has to equal sigma times L, because that's its units, which in this case is sigma pi times little d. But we need a component of force in the plus z direction, so we kind of have to know what that wetting angle is alpha. So we'll leave that as unknown for the time being. So we do a force balance in the z direction. We have F sub sigma sine alpha minus W is equal to 0. And so the pi d squared times the height of the column times rho g is just the weight of the water column itself. And then here is the surface tension force at the top. And we solve for delta H, and we get 4 times the surface tension sigma times the sine of alpha divided by rho g divided by d. So that is our equation for capillary rise in terms of surface tension and the capillary tube diameter. There's some intermediate algebra shown below, but we're going to go right to the bottom of it. Oh, you're getting lucky. The computer battery is almost toast, which is good because there's only 9 minutes left of you having to endure me. The intermediate algebra is shown there, but the important thing is the contact angle for water is almost pi over 2. So we can take advantage of that. The sine of alpha for water is almost 1. We will treat it as 1. And with that, our capillary rise in water is approximated with this expression here, 4 times the surface tension divided by the specific weight of water divided by the diameter of the capillary tube. So if our goal is to predict how high it rises in a capillary tube, we need to know the surface tension and the diameter of the tube. If our goal is to measure surface tension, we need to know the diameter of the tube and how high it goes up in the tube, which is why they stick that onto your blood when you go to give blood to see if your blood has the right surface tension for whatever machinery they're going to sell it to. So let's suppose we had a diameter of 0.16 millimeters, surface tension of 0.07 newtons per meter, water of 9,800 newtons per meter cubed, and we want to figure out how high it goes. Let's simply put the numbers in the formula, and we come up with, this one is probably the one that has the mistake, 18.6 millimeters. Not very much. My tube is too big a diameter. But you get these tubes small enough, like the kind of tubes that are made in a clay soil by the interconnected porosity, you can get several meters of capillary rise. Any questions on that? That should be pretty straightforward. And here's what I did just before I came over today as I burnt up my computer. A viscometer. I didn't know the spelling myself. There's a variety of instruments used to measure viscosity. They all operate more or less on the same principle. They operate pretty much the principle of that block sliding down a plane. Although if we're going to charge people $22,000 for an instrument, we've got to make the blocks out of really cool stuff and have lots of digital readout. So back in the olden days, some dude named Oswald had a YouTube viscosimeter. I haven't read carefully how it works. I know that he's being sued by the Alphabet Corporation for violating their copyright principle for YouTube spelled differently. But this guy got his Nobel Prize in 1909, so I think he's going to win the lawsuit, or his estate will. A falling sphere viscosimeter. This uses Stokes' law, which you get in the chemistry and environmental engineering class, where you drop a sphere down and it goes at constant speed. The viscosity is what controls how fast that goes. And that's attributed to some guy named Stokes. He was pretty stoked. There's a falling ball viscosimeter, which you may have seen, same kind of idea. A falling piston viscosimeter, which I have a work problem on, and then oscillating, vibrational, just about any way you can make fluid move between two known geometries and determine the force required to make that happen is what causes is a viscometer. The science of measuring these kind of things is called rheology, R-H-E-O-L-O-G-I, and actually that's a it's not a hugely populated field, but it's something you somehow get interested in. Not because of me, that's for damn sure. There's a good future in rheology because they work for oil companies and similar corporations to create new materials that are used industrial. Here's an example problem. This would be called a falling piston viscosimeter. And like all fluid mechanics problems in the history of the world that are taken out of books, they always ask the wrong question. So the correct question should be, in the falling piston viscosimeter, dimensions are given, the weight of the piston is though that falls at a certain speed, what's the viscosity? Oh, no, that's not how they ask the question. They tell you the viscosity, you're supposed to find the speed. So it says, derive a formula for the steady rate of descent of the cylinder with weight W, diameter D, length L, sliding inside a vertical smooth pipe that has inside diameter cap D. Assume the cylinder stays concentric with the pipe as it falls. Use your formula to estimate the rate of descent for a cylinder 100 millimeters in diameter that slides inside a 100.5 millimeter inside diameter tube. The cylinder is 200 millimeters long, weighs 15 newtons. Here's where they get you. And the lubricant is SAE 20 weight oil at 10 degrees Celsius. Now, how do you find the viscosity of SAE 20 weight oil at 10 degrees Celsius? How do you do it? It's not a trick question. How would you do it? Someone said Google it. Yeah. 15 years ago when I created these, how did you do it? You had to go look in the back of the friggin' book and find the table that had it. Google is way faster for this kind of stuff, and that's what it's awesome for. But we'll just go through the solution really quickly. So if you were to do an abbreviated form of that, you draw your sketch, you write your unknowns, you write your knowns, you go look up what the viscosity of that particular oil is, 0.35 Newton seconds per meter squared. Your first cut, which would be legitimate, would be to assume we'll neglect the buoyant force. In the real one, there will be some buoyancy conferred by the oil to the object. And then write a governing equation. The definition of viscosity, carries with y, and a force balance of the falling piston, falling at constant speed, which is this the second part here, or equating the weight to the frictional or the viscous resistance force. And then the solution would be apply some of that algebra stuff, and then finally come up with a velocity in terms of everything else, and we get 0.17 meters per second. And if you cared, you could easily write a tool, script a tool that would actually let you have a falling piston viscosity. You can imagine. Now, how could you build one? Let's say you had a need to build one. What would you use for your outer tube? There's no way no one here has not been in Home Depot. There's a whole aisle there, a plumbing aisle, got all sorts of pipes and shit. Pick one. Okay, what do you use for your piston, falling piston? I would use something different. Different aisle in Home Depot. That's the one that has the little metal bits. You just go get a good old solid metal bit, or get a big old 3/4 inch piece of all thread, and grind the threads off. That's a really stupid use of a grinder. And now you have your piston. Cut it to a appropriate length, and you fill your thing with oil. You drop it. You wait till you hear it clunk at the bottom. Stopwatch. That gives you the time. You know how long it is. You have velocity. So these you could actually really build one. And then there's a computer program that you could use to provide the digital readout when you build it. There's not much to it. All it really is that equation that's above rearranged in terms of viscosity. The boron says about velocity because people write the questions in your book. What we care about is viscosity. This is how you would build one viscosity. Now, I don't think you can get $22,000 for it, no matter how cool the digital readout is, even if you had bells and whistles and put wheels on it. But if you had a need to, you could measure viscosity of probably things like water, oil. What else would you need to measure viscosity? Concrete before it gets so viscous and it's hard. Things like that. Lastly, I will close off in 0 minutes or less with vapor pressure. Vapor pressure is the pressure exerted by vapor and thermodynamically. So if you take a liquid and you put it in an enclosed container and it has headspace, some of the molecules of that liquid will go into the gas phase. It will exert a partial pressure inside that headspace. That partial pressure is called the vapor pressure of the liquid. It's temperature dependent. So let's suppose the liquid is ethyl alcohol. It's hydrogen. And we do it at slightly above freezing. So is the vapor pressure going to be high or low? Comparatively. Are you even going to be able to smell that process? I'd say no. But if we start to heat it up and we get it close to 80 degrees Celsius, home without your table of alcohol boiling points, it's pretty close to the boiling point of alcohol. A lot of it is going to go into the vapor phase. And partial pressure is called the vapor pressure of the alcohol. Now it matters in ours is in two places. First is it kind of matters in barometers. When you make a barometer and you invert it, you have a headspace up here, which is, starts out evacuated, and it's just the chemical that's whatever the fluid is in the barometer. So it could be water, it could be oil, it could be liquid. And so the vapor pressure of that matters. So measuring atmospheric pressure depends on temperature. The other place that they measure is in things like pipelines, where we get negative gauge pressure. If the pipeline going up over a hill, you can sometimes get negative pressure. If you get too negative, and the pipeline doesn't have water, let's say maybe it has oil in it, something else that burns, good gas on it, gets too negative, all the liquid will flash into the vapor phase. We call them vapor locks. You either stop the flow, which would be undesirable or not the end of the world, or it can find a source of ignition, something like acid, which it will, and it goes boom. And the part of San Juan, Puerto Rico in the 80s blew up because of something like that. A bunch of volatiles got in there, changed phase, found the source of ignition, and that's all she wrote. All right, well, thank you all for paying attention and at least pretending to stay awake. I applaud you for that. We will resume on Thursday where we start fluid statics and pressure. Has anyone who's tried to upload the homework had trouble doing it? Yeah, you can do it on paper, take a picture of it and upload the picture. All right. Absolutely. Oh. Hopefully we'll get the recording done.